Welcome to part 2 of the lecture on local optimizations. In the last lecture, we learnt about basic blocks, control flow graphs, a few of the optimizations as examples and how to build a flow graph. Today, we will continue in the same direction, learn what directed acyclic graphs are and understand value numbering. So, just to recapitulate from the last lecture, here is an example of a control flow graph. So, these are the basic blocks, each basic block is a single entry single exit structure and there are arcs between the basic blocks to show the control flow within the program. The contents of each of these basic blocks are quadruples, that is a form of intermediate code, and these basic blocks and are built by identifying leaders, and there are optimizations which can be carried out on these basic blocks, which we are going to learn from now on. Okay. Here is an example of a directed acyclic graph, DAG as it is called. Here is a set of 10 quadruples, a small basic block, and a basic block can be represented in the form of a directed acyclic graph. Here is the DAG representation of this particular basic block. So, why are we studying this representation of a basic block? First of all, this is the conceptual structure that we need to build in order to perform local optimizations, and it very clearly tells us what are the capabilities of such an optimizer. So, let us go quadruple by quadruple and see how this particular DAG structure is built. The first one is a equal to 10. So, here is a node A, a node containing 10 and it is labeled as A. So, this is the way we are going to do it. Whenever there is a value or whenever there is an operator star plus etcetera, that is going to be placed inside the node as text, and there is a label attached to each of these nodes which will tell us what is the name associated with that particular value or operator. So, A equal to 10 corresponds to this particular node with the value 10 inside and the label A outside. So, the next one is B equal to 4 star A. So, here is a node containing value 4, the node star connects 4 and A, and it is by itself named as B. The next one is the one equal to I star j, which is very similar. There is a node I and there is a node j. These names are also put inside because there is no value attached to them as of now, and then there is a star which really shows that I and j are connected, and the value the label associated with the node star is T1 to begin with, T3 arrives later. C equal to T1 plus B is similar. T1 is used as one of the children of plus, B is used as another child and it is labeled as C. This overstriking of C has an extra meaning which will be clear later on. T2 equal to 15 star A is similar, A is reused, 15 is created, star is created and a label T2 is attached to this particular star. D equal to T2 star C, again we take T2, we take C, and then these two are related by star and that is actually labeled as D. There is another statement E equal to I. So, there is a node already with a value I or a label I, and there is no modification of that I which has been carried out. So, the value of E will be the same as value of I before, and it is also therefore, we attach the label E to this particular node I and nothing else, no other action is taken. T3 equal to E star j. So, E star j is actually discovered as I star j because E is nothing but a label on the node I, and therefore, I star j and E star j identical, the I star j small subtree already has a label T 1, and therefore, T 3 is also attached to the same list of labels. So, T 1 and T 3 are both now corresponding to this particular star. There is no further node creation which is carried out. So, this is an example of how common sub expressions are actually discovered. So, I star j was an expression which was computed. Now, E star j, which is nothing but I star j, has also been discovered as a common sub expression. So, we do not have to compute it again, we just use the previous expression, and this is indicated by attaching the label T 3 to this particular node star. T 4 equal to I star A. So, this is really at this part of in this part of the picture. So, there is A, and this is already I is already here. So, now there is something special which happens here. Look at it, the what is stated here is I star A, and what is taken here is A star I. So, this is possible because we assume at this point that the star operator is commutative. So, by using commutativity, we checked whether if I star A was not present. So, we checked whether A star I was present. So, we discovered that A star I is present, and therefore, we A and I are present rather, and we created a node star and attached a label T 4 to it. C equal to T 3 plus T 4 is very similar. There is T 3 here, T 4 here, and this is an example where a new value has been assigned to C, and the old value in quadruple number 4 is no longer going to be used. So, this is overriding that particular value. So, this old value is killed, the node label C is deleted, and a new label C is attached to this particular class. So, this DAG hopefully shows examples where there is a reuse of nodes, and that common sub expressions are discovered and so on. So, now let us see how to implement this type of a scheme to carry out some of the local optimizations. Value numbering is a simple way to represent DAGs, and while searching the directed acyclic graphs, if we represent them using pointers etc., it is extremely inefficient. For example, if you are searching for a node in the DAG, it is not possible to search for the node without exhaustively searching the entire DAG. So, so in practice, when we implement optimizations on DAGs, we use the value numbering scheme rather than a linked representation of DAGs. Value numbering scheme uses hash tables, and therefore, it is very efficient in searching the graph itself. What is the central idea? The central idea of value numbering is to assign numbers these are called value numbers. So, these are assigned to expressions, and of course, they are also assigned to single variables in such a way that two expressions receive the same number if the compiler can prove that they are equal for all possible program inputs. So, we saw this happen in the previous picture, only thing is we had not assigned any value numbers. So, for example, here I star j was already present. So, E star j was discovered as a common sub expression. We will soon see that this particular expression I star j and another expression E star j will both receive the same value numbers. So, what we assume are quadruples with binary or unary operators. We also permit copy operations, assignment of constants and so on and so forth to variables. There are three tables which are used by this particular algorithm, and they are all hash tables. So, I will show you some pictures of these data structures very soon. The first one is called a hash table. The other one is called as a value number table, and the third one is called as a name table. So, let us see some pictures. So, here is a hash table entry. It is indexed by expression hash values. In other words, we take an expression, hash the expression, that will give us some particular value index, and go to that particular index in this hash table. If the expression which is present there is the same as the one we are searching, then there is success, and if there is no success, if necessary, we insert that particular expression into that index. So, in each one of these entries we store the actual expression itself and the value number. Value number is nothing but a counter. So, we initialize it to 1 and then we go on incrementing it whenever we need a new value number. So, this is so far as the expression hash table, as a hash table which is storing expressions. Then the second one is called a value number table. A value number table is shown here. Each entry actually has a name and a value number. This is indexed by the hash value of the name. Why do we have a separate val number table, and why do not we store names also in the hash table itself? The hashing function for expressions will have the two variables of the expression, assuming that it is a binary expression, binary operator. So, it will have as parameters the two operations, rather sorry, the operands. Let us say in A star B we take A and B, and then the operator also, the star, has to be incorporated into the hashing function. So, depending on the three values A, star and B, the index value produced is going to be different. If they are different variables, again it is going to be different. So, the same expression hashing function cannot be used for names, where you do not have any operator and you do not have a second name. So, we use a different table for storing names, and this is the value number table. For each name you hash it, then you produce, you go to that particular index and pick up the value number if the name is already present there. The third one is called as a name table. So, name tables are shown here, the entries are shown, an entry is shown here. There is a name list, there is a constant value and there is a constant flag. So, a name which actually produces it is indexed by the value number, for example. Okay. So, the names are given value numbers, and the value number is used to index into this particular table called the name table. So, inside the name table we store the constant value of that particular name if it is a constant, and then set the const flag to 1. If the name that is stored here is not a constant, then this is set to 0, and then this particular field has no relevance. But what is this list here? So, in the field name list, first name in the list is always the defining occurrence of that particular name, and it replaces all other names with the same value number with itself, okay, or its constant value. So, if there are many names which are equivalent, we saw this happen in this particular figure, T1 and T3 are equivalent, all right. So, here E and I are equivalent, and so on and so forth. So, in such a case we are going to have a list of such names here which are equivalent, and the first one is the defining occurrence, which will be used in place of all other names in that particular list, and if it is a constant, we are going to use that value of that constant in place of all these names. The value numbering scheme can be used to eliminate common sub expressions. Constant folding can also be performed, and constant propagation can be carried out in basic blocks. So, elimination of common sub expressions is something which I already mentioned. Constant folding is evaluation of expressions involving only constants, and constant propagation is if there is a assignment which says A equal to 4, then wherever A is used, 4 is going to be propagated to that point, that is called constant propagation. We will see how to do these things with value numbering. Value numbering can also take advantage of the commutativity of operators, which I briefly mentioned a few minutes ago with respect to that directed acyclic graph representation, addition of 0 because a plus 0 is a itself, multiplication by 1, a star 1 is a, and these are the three which have a simple algebraic laws which can be taken care of by value numbering in basic blocks. So, let us take an example, run through that example in a step by step fashion and see how it works out. Here is a high level language program, a equal to 10, b equal to 4 star a, c equal to I star j plus b, d equal to 15 star a star c, e equal to I and c equal to e star j plus I star a. So, if you look at this, here is a equal to 10. So, this is actually the, if you observe, it is the same program that we saw here, okay. There is no difference. So, only thing is we had considered the quadruple version directly, here is the high level language version. So, I star j plus b is broken into 2 quadruples, 15 star a star c is also broken into many quadruples. Similarly, this is also broken into many quadruples. So, what is the set of quadruples after the optimization? So, let us understand that and then see how the optimization itself is carried out. So, a equal to 10 remains. In 4 star a, b equal to 4 star a is 10. So, we are going to replace it by b equal to 40. T 1 equal to I star j remains as it is. C equal to T 1 plus b, b is replaced by 40 which is now being calculated as a constant. T 2 equal to 15 star a becomes T 2 equal to 150 because a is a constant value of 10. D equal to T 2 star c becomes d equal to 150 star c because T 2 is 150. E equal to I remains as E equal to I and T 3 equal to E star j becomes T 3 equal to I star j. It is really now we find that T 1 equal to I star j and T 3 equal to I star j actually are the same, one and the same. So, we can delete this particular instruction number 8 and always use T 1 in its place. So, further T 4 equal to I star a becomes T 4 equal to I star 10 and C equal to T 3 plus T 4 becomes C equal to T 1 plus T 4 because T 1 and T 3 have the same value. As I said, 8 can be deleted and T 2 equal to 150, the value of 150 has already been propagated to all the other places. For example, T 2 star C is the only place where T 2 is used. So, this quadruple is not needed anymore, 5 and 8 can both be deleted and we have detected that I star j is a common sub expression. We have done constant folding by evaluating these expressions, constant expressions, and we have done constant propagation by replacing these b's and a's by constants. So, let us see how all this can be done. So, the first quadruple is a equal to 10. Now, a is entered into the ValNum table, let us say with the value number of 1. This is the beginning. So, we have set V n the counter value as 1 and it is also entered into the name table with a constant value of 10. So, first a is hashed, entered into ValNum table, the val number is set as 1 and then using that val number index into the name table, set the constant value as 10 and set the constant flag as 1. Second quadruple b equal to 4 star a. So, now when we search for a in the ValNum table, which is a variable, we find that it is already present and its value is 10. That value can be found from the name table by using this value number in the ValNum table. So, we have performed now constant propagation because we find that a is 10 and we can replace it here. 4 star a is evaluated to 40, this already said, and the quad is rewritten. This is the other action. We have now performed constant folding. B is entered into the ValNum table with a value number of 2. This is a different value number now, and into the name table using the same value number of 2 with a constant value of 40. So far, we have entered these two into the appropriate tables. T 1 equal to I star j is similar. I and j are not present in the tables. So, they are entered into the tables. new value numbers are created, okay, and there is no constant value attached to either I or j because they are not constants. I star j is entered into the hash table with a new value number. So, we hash this, go to that index, store it and assign a new value number because I star j was not present before. T1 is entered into the ValNum table with the same Vn as that of I star j. So, we assigned some value number to I star j, the same value number is assigned to T1 because these two always carry the same value until this point in time. E equal to I. I is already present thanks to I star j, I was introduced into the table some time ago. So, we get it actually from the table, find the value number and then assign the same value number to E as well. So, whenever we get E, we can replace it with I. So, what we do is this actually is entered into that name table along with I, I is the first defining entry and then E is going to be attached to the same list. In processing T3 equal to E star j, we find that E and I have the same value number, search and you get the same value number. E plus j is nothing but I plus j, sorry, E star j, this plus is a mistake. So, E star j is same as I star j and since I star j is already in the hash table, we have found a common sub expression. So, please read this plus as star. From now on, all uses of T3 can be replaced by T1. So, T1 was already present in the hash table, right. So, there is no need to create another sub expression called I star j. Quad T3 equal to E star j, which is nothing but I star j, can be deleted. So, we found that I star j is present, its T1 is actually attached to it with the same value number. So, now we have the same value number attached to T3 also and therefore, T1 and T3 are two occurrences of the same expression, we have two occurrences with the same value number. So, whenever we have T1 we can replace, whenever we get T3 we can replace it by T1. So, T1 and T3 will be entered into the name table, T1 as the defining occurrence and T3 following it. Now, C equal to T3 plus T4. T3 and T4 are already there in the table and they have a value number 2. So, T3 plus T4 is entered into the hash table with a new value number. So, we hash it and enter, this is not in a common sub expression which is already present. This is a reassignment to C, that is what we need to be very careful about. You see, so far we had this is not the third quadruple, this is really the quadruple a little later on. Okay. So, this is the sixth quadruple. Okay. So, T3 plus T4 was not there, so we have entered it, but this is a new C, this is not the same old C. C was defined earlier, but now C is redefined. So, C gets a different value number and it is the same as that of T3 plus T4. So, the old C actually it is kind of disabled, its value number is not used anymore, it is rewritten with the new value number. So, these quadruples are all renumbered after the deletions and we get an optimized set of quadruples as we saw here. So, 5 and 8 go away, 5 is gone, 8 is gone. So, then we make 6 as 5, 7 as 6, etcetera, etcetera, etcetera. So, here are the hash table and value number table at finishing time. So, see that I star j has value 5, T1 plus 46, 150 star C has 8, I star 10 has 9, T1 plus T4 has 11. So, these are the various expressions that we have found with distinct value numbers. Value number table is interesting, A, B, I, J, T1 and C, they were all given 1, 2, 3, 4, 5, 6. Then T2 7, D is 8, E did not get a new value number, it got the same value number as 3. Then T3 did not get a new value number, it got the same value number as T1 and then T4 got a new value number 10. the second time C got a value number 11 and the 6 was overwritten. Here is the name table at the end. So, A is stored with constant value 10 and const flags true, B is stored with 40 and true, I and D are not constants. So, there is nothing here, J is not a constant, T1, T3 are not constants. So, please see that I and E are together here. I is the defining occurrence and replacement for E will be that of I. Similarly, T1, T3 replacement of T3 will be T1 itself, T2 is 150 and true, D and C are not constants. So, this is how we do simple value numbering and create these tables, find common sub expressions and so on and so forth. Now, let us see how to handle commutativity. So, when I already mentioned this commutativity in the directed acyclic graph representation. So, when we search for an expression I plus j in the hash table and this search let us say fails. So, if plus is commutative on integers, for example, commutativity holds, on floating point numbers it may not hold. So, let us assume that commutativity holds. So, now instead of if I plus j is not available, we search for j plus I. So, perhaps j plus I is present. So, we already saw this happen before. If there is a quadruple, so this is using commutativity, exploiting commutativity. If there is a quadruple x equal to I plus 0, then it is not necessary to keep it as it is and do the arithmetic with plus, it can be replaced with x equal to I. Perhaps from now on, we can use I in place of x and finally even x can be deleted. So, here we are using an algebraic law, a equal to a plus 0. Any quadruple of the form y equal to j star 1 can be replaced with y equal to j. This is again a simple law, a equal to b star 1, right, can be replaced by a equal to b. After the above two types of replacements, value numbers of x and y become same as those of I and j. So, that is a very simple thing to see. Quadruples whose LHS variables are used later can be marked as useful and all unmarked quadruples can be deleted at the end. So, this is the implementation detail. There are more complications which come in when there are arrays. So, let us consider a simple sequence of 3 assignments: x equal to ai, aj equal to y and z equal to ai. So, if you look at this particular statement aj equal to y, I and j are runtime variables, right, they can take any value. So, we have no idea of what their values are. So, it is possible that I and j could be the same. If they are same by some chance, then I is not a common sub expression anymore. Syntactically this ai and this ai look the same. So, I could have possibly said z equal to x if we had only looked at the syntax, but this particular statement aj equal to y, if I and j are the same, should be interpreted as ai equal to y, in which case there is a reassignment of value to ai and the previous value which was assigned to x cannot be used as the value of ai anymore. So, we need to retain these 3 statements as they are. So, this is a problem. How do we handle it? Whenever there is an array expression, we actually do not try reusing the value of that array expression at all. So, the above sequence cannot be replaced by x equal to ai, aj equal to y and z equal to x because of the reasons I mentioned just now. So, this is processed as it is. Here is an indexing assignment operator. So, we hash this particular expression ai, enter it into the tables and then x is taken as a defining occurrence which gets the same value number as ai. But when we process aj equal to y, all references to array A so far are searched in the tables. We need to search exhaustively, there is no other mechanism, and they are marked as killed. So, this kills the quadruple number 1 here. So, there could have been others also. All such AI, AJ, AK, AX etc. are all deleted, rather marked as killed, so that their value numbers are not reused from this point onwards. Why? This particular j could have been any one of those values. We do not know which value it is. It could be, it could possibly is not, but we cannot take a chance. When processing z equal to ai, killed quadruples are not used for common sub expression elimination. So, fresh table entries are created for z equal to ai. There is a new value number which is assigned to ai. However, if we know a priori that I not equal to j, so that these two are never identical, then ai can be used as a common sub expression in this particular case, but this is very rare, it is very rare. So, we may have to kill them. Pointers are very similar. So, consider x equal to star p, star q equal to y, and z equal to star p. So, p and q could be pointing to the same object, you do not know, at runtime this can happen. If it has happened, then z equal to star p is not a common sub expression anymore, because a new assignment is being made to star q. It is not x equal to x was pointing to what p was pointing to, x contains star p. So, x contains the object p was pointing to. Now, a star q contains a new object y. So, q points to a new object called y, and it is q has a value possibly p itself. So, this should be read as star p equal to y. So, now p points to some other object, and therefore, z equal to star p cannot become x, z equal to x, this would be wrong. It is very similar to the array case before. So, if pointer analysis has been carried out and p and q never point to the same object, and that fact is known, then we can proceed with the same CSC here, but otherwise p and q can point to any object in the basic block. Hence, when star q equal to y is processed during value numbering, all table entries created so far are marked as killed. So, this kills the quadruple number 1 here, and when we are processing z equal to star p, killed quadruples are not used for CSC, and fresh tables entries are made for z equal to star p. Something similar happens when we have procedure calls. So, if we do not know a priori which objects p and q point to, then table entries corresponding to only those objects need to be killed. So, this I mentioned already. So, what happens in procedures? With no data flow analysis, that is analysis of the program, we need to assume that a procedure call can modify any object in the basic block. So, if the procedure is called, it has side effects. So, it can assign to global variables, it can assign to parameters which have been passed by reference. So, we have to assume that any variable in the basic block is modified, because we have not carried out any analysis and we have no information about any variable. Hence, while processing a procedure call, all table entries created so far are marked killed, everything goes, nothing is visible anymore, nothing is useful anymore. Sometimes this problem is avoided by making a procedure call a separate basic block. So, we eliminate this problem, we avoid it by making a separate basic block for a procedure call, so that it does not kill any other variable, and since the procedure call is in its own basic block, this is a fairly simple thing to do. So, analysis becomes much simpler. Now, we looked at basic blocks. So, sometimes basic blocks are small. So, what happens is all the techniques that we have applied may not be so effective. there is a way to extend whatever we did so far with the value numbering to a sequence of basic blocks. Let us see what these are. A sequence of basic blocks B1 to Bk such that Bi is the unique predecessor of Bi plus 1 for 1 less than or equal to I less than k, and B1 is either the start block or has no unique predecessor. So, such a sequence of basic blocks is called as an extended basic block. So, extended basic blocks with shared blocks can be represented as a tree. So, let us look at some examples. Here is a control flow graph, right. So, start B1, B2, B3, B5, B7, this side is B6, B7, this side is B4, B7 and then stop. So, the extended basic blocks are start and B1, okay. And then when you go to B2 it has two predecessors, it does not have a unique predecessor. So, we stop our extended basic block at B1 itself. Then you consider B2, B3 and B5, B2, B3 and B5. Okay. So, if you try adding something else, for example, B7, then it has two predecessors. So, we really cannot have that in the same basic block, right. So, B2, B3 and B6, this is another extended basic block, this is a sequence. We could not have added B2, B3, B5 and B6 because B5 and B6 are not in the same sequence. Okay. So, B2, B3, B6 are all B5 is not the predecessor of B6 or vice versa. So, we cannot add these two in the same extended basic block. So, B2, B3, B6 forms another extended basic block, then B2, B4 forms one more extended basic block. Finally, B7 and stop form a basic block, extended basic block. Now, these three B2, B3, B5, B2, B3, B6 and B2, B4 actually share basic blocks. So, B2, B3 is shared with B5 and B6, B2 is shared between B3 and B4. So, there is a lot of sharing that happens in these, right. So, because of this B2 is shared in all of them actually, B2, B3 and B5, B2, B3, B6, then B2, B4. So, B2 is shared in all of them. Now, such a tree representation can be used gainfully to do our value numbering and extend the benefits of value numbering to such basic block trees. So, what we do is very simple. We really need to use a technique which was used in the symbol table construction for programming languages with nested scopes. So, the new entries, okay. So, shared blocks in extended basic blocks required scoped versions of our tables. I will explain what these are. The new entries must be purged and change entries must be replaced by old entries as we go on, and a pre-order traversal of extended basic block trees is used here. So, let us see what happens. So, we start let us consider this particular set of extended basic blocks. So, we start our value numbering with the basic block 2. It is done as usually, as is usually done. The expressions and variables are entered into the various tables and they are filled. When we come to, then we take up B3 without destroying any of the tables built in B2. It is easy to see that we can use all the common sub expressions and constants of B2 in B3 also. There is no problem at all. So, we can keep the entries of B2 and reuse them within B3. Now, when we go to B5, something similar happens. We can reuse the entries of B2 and B3 with no difficulty at all. But once B5 is completely processed, possibly we have discovered new common sub expressions and constant propagation, folding etc. has been carried out using B2 and B3 also. B5 is completed. So, now we have to get back to B3 and start processing B6. This is the pre-order traversal, but the entries that we actually created during B5 cannot be made available during the processing of B6. We need to have only the entries of B2 and B3, and the entries of B5 must be eliminated, removed. This is the reason why we require scoped versions of these tables. So, we start a symbol table, we use something similar to scoped symbol tables. We have a set of tables at scope equal to 1. When we come to a new level, we actually establish tables at scope equal to 2, and here we establish tables at scope equal to 3. Whenever we want to search these scope tables, we actually search for the current tables, search the current tables first, then in the enclosing scope, and then in the next enclosing scope, and so on and so forth up the tree. When we finish processing B5, all the tables with scope equal to 3 are removed, and a new table with scope equal to 3 is started for B6. So, now we use entries of B2 and B3 in B6 also. Finally, when B6 is completed, its entries are all deleted, we go to B3, when we need to now return to B2. So, the entries of B3 with scope equal to 2 are also removed, a new set of entries with scope equal to 2 corresponding to B4 are created, this is processed, and finally, we return to B2 after deleting the entries corresponding to B4. So, this is how scoped hash tables are used in order to do value numbering on these extended basic blocks. As you can see, because we reuse entries from B2 and B3 in B5 and B6, there is a lot more scope for discovering common expressions and finding constants, doing constant propagation and so on. Here is a simple algorithm for doing value numbering. So, when we visit extended basic block tree, and E is a node in the tree. So, it is to begin with the root of the tree, and from now on the new names will be entered into entered with a new scope into the tables. When searching the tables, we always search the beginning with the current scope. This is something I already mentioned, and move to enclosing scopes. So, this is similar to the processing involved in symbol tables with lexically scoped languages. So, value number E comma B is the call to the function value number to process the basic block B, and now, so E dot B is the basic block. So, E dot left not equal to null, then visit left subtree, E dot right not equal to null, visit the right subtree. This corresponds to the pre-order traversal. Then once the left and right subtrees are completed, remove the entries for the new scope from all the tables and undo the changes in the tables of the enclosing scopes. So, this is the function called visit EBB, and which is actually called for each tree representation of the extended basic block. So, this brings us to the end of the lecture on local optimizations. So, welcome to the lecture on code generation. So, in this set of lectures, we are going to look at the main issues in machine code generation, some samples of generated code, two schemes for generating simple code. So, these are simple code generators. Machine code generation is a very fascinating area with several optimal code generation algorithms. We are going to look at a couple of algorithms of this kind. One of them is the historically famous Sethi-Ullman algorithm. Then there is a slightly more complicated dynamic programming based algorithm, and we are also going to look at a practical tool called iBurg, which uses tree pattern matching and dynamic programming in its implementation. Then we are going to look at the method of generating code from directed acyclic graphs. This problem is NP complete, so we need some heuristics to solve this problem. Finally, we will talk about peephole optimizations, which are machine dependent optimizations. What are the main issues in machine code generation? Machine code generation is a transformation. So, it transforms intermediate code to machine code, and machine code we can say is either binary representation or assembly language representation. If it is a binary representation, all the machine code which is generated for the program can be sent to the linker and then the loader, whereas if the machine code is in the form of assembly, it has to be sent to the assembler, which in turn generates binary, then the binaries are sent to the linker and the loader. But the difficulty of generating code is the same whether we generate machine code in binary or machine code in assembly. It is just that if we want to generate binary, the job of doing assembly is also in some way incorporated into the machine code generator itself. Let us assume that we generate assembly, because it is easier to explain the scheme in such a case. Let us assume quadruples as our intermediate form, and let us also assume that the control flow graph is available to us. The first issue is which instructions should we generate. So, for example, let us say the quadruple is a equal to a plus 1. A very simple instruction such as increment a can be generated, or we can say load a into the register R1, add the constant 1 to R1 and store the register R1 in a. So, either one instruction or 3 instructions. Well, obviously increment is much cheaper, as everybody can realize, but if there is no increment instruction in the instruction repertoire of the machine, we need to generate this particular sequence. The point here is every machine is different, its instruction set is different. Therefore, we cannot assume the existence of a particular type of instruction in every machine. We will have to, our algorithms for code generation will have to cater to every type of machine. What we know is that every machine will have instructions to perform any task, that is all we really know. So, here this increment, one of the sequences may be faster than the other, and in such a case we say that one of the sequences is cheaper than the other. Second issue, in which order should we generate code? It is possible that some of the orders use fewer registers and some of the orders may also be faster than the others. So, the code generator to some extent must evaluate different orders and then choose the best. Obviously, it cannot enumerate all orders and check them. It uses other mechanisms to check a few of these orders and finally choose the one which is cheapest. One more issue is which registers should we use in code generation. Some of the registers are reserved for particular types of use. For example, the program counter, the stack pointer. So, these are specific registers which should not be used for any other purpose. This is the norm in programming. But there are many registers in machines, and these registers can be used to store any variables. So, which registers to use, which variables should we put in those registers, etc., is the problem of register allocation in general. So, optimal assignment of registers to variables is very difficult to achieve. There are heuristics which are used to achieve this with some efficacy. One other issue is, should we optimize for memory Should we optimize for time or should we optimize to save power? Each of these is actually very important in a different context. For example, for embedded systems of one kind, okay, it may be necessary to save memory. So, we must optimize for memory. In another embedded system such as sensor network, the programs which run may have to actually save power because they all run on batteries. And in our servers, it is necessary to optimize the programs to save time. So, they must run as fast as possible. Power and memory are not considerations here. So, which the code generation strategy for any type of optimization is going to be different. So, the cost of the instruction sequence is abstract. So, it can be memory save space or time or power. We will see how this is done. Is the code generator easily retargetable to other machines? Is a very important problem. Writing code generators is a difficult task, it is no easy task. There are thousands of details which need to be kept track of. It is necessary therefore, that code generators be produced either automatically or parts of code generators be used in writing code generators for other machines. So, can the code generator be produced automatically from specifications of the machine? So, as we will see later, it is possible to use what are known as tree grammars for the specification of the machine instructions, and there is going to be a code generator which is very similar to Yacc. Yacc accepts context free grammars and gives you a parser. This type of code generators accept such specifications and produce code generators as output. So, let us look at some samples of generated code to understand what the issues are. We have shown here several types of quadruples. B equal to AI is actually loading B from an array. Xj equal to Y is assigning a value to an element of an array. X equal to star P assigns X a value using a pointer. Star Q equal to Y assigns a value to a location pointed to by Q, and here is a branch statement. So, let us see what the code that is generated for each of these. B equal to AI. So, load I into R1. So, now the value of I is available. What is I? It is the offset within the array A. Multiply R1 by 4 and then put the value in R1 itself, Y. Each of the elements of the array is assumed to be 4 bytes long. So, if you look at the byte version of the array A, each value is stored in blocks of 4 bytes. So, to get to the ith location of the abstract array A, we actually have to pass 4 star I locations. So, that is what is done by multiplication here. So, 2 instructions already just for this particular thing. Finally, load A of R1 with R2. So, sorry, the other way, load R2 with A of R1, R2 equal to A plus R1. So, what we really contents of A plus R1. So, what we really did was take the index which is R1, go into the array A, get the contents of that particular location, now it is A of I, and place that into R2. Store the value of R2 finally in B. So, this 4 instructions actually are required to satisfy this one quadruple instruction. Similarly, Xj equal to Y is simple. We have load Y with R1. So, load Y into R1, then load J into R2. Now, we need to compute the address of Xj. So, multiply R2 with 4 and place it in R2. So, now we have gone to the place in x where we need to store the value of y. So, R1 contains y. So, store R1 into x of R2, this will store the value y into x of j. So, x equal to star p is simple, load p into R1, and now load 0 R1 R2 comma R2 takes the contents of R1 as an address and goes to that location, fetches the value in that particular location and puts it into R2. So, an indirection here. Store R2 into x puts this entire value which is in R2 into x. Star q equal to y is very similar, load y into R1, load q into R2, store R1 into 0 of R2, this is actually indirection. If x less than y go to L, so load x into R1, load y into R1, now compare R1 and R2, if branch on less than 0 to the label L. So, these are some of the examples to show what kind of code that we need to generate. So, in the next lecture we are going to look at samples of static allocation, dynamic allocation, and then see how to generate such code using simple methods and also with optimal methods. Thank you.